This time in the shop, let's talk about building your first wire antenna, and let's build a balun box. Okay, wire antenna building part 3. Today we're going to talk about actual designs, and we'll go over some of the different horizontal dipoles that you can build. And by the way, all these antennas are easily buildable by anyone. There's nothing fancy going on here. Anybody can grab some wire and put together a balun box and put these things in the air and they'll work just fine. You don't have to have fancy insulators. You don't have to have fancy wire. You don't have to buy the baluns. You can build them yourself. This is really easy stuff. And I'm actually on my 5th wire dipole. So anybody can build these things. It's not rocket science. You do need some sort of an antenna analyzer. You're going to need an nano-VNA or an antenna analyzer. It's almost impossible to do this without one. I mean, it's not completely impossible. You could do SWR sweeps with the radio, but that would be very tedious and take a very long time and is definitely not the ideal solution for tuning antennas, although I have done it that way. It just takes a lot of time. So we'll start with the easiest antenna that you can build. The easiest antenna that you can build is a simple wire dipole that's an inverted V. And in this instance, we're going to use a 40 meter inverted V dipole. So the legs on this are 31.2 feet. Actually a little longer, 31.7 feet, because the center part is where I put the feed on this antenna, and that's about a foot. 31.7 feet times 2 is 63.4 feet total length. And this antenna is not very high off the ground. It's only 28 feet off the ground. The ends of it are only 20 feet off the ground. And when you model it, you can see it's just a big ball of RF. This is not a distance pattern at all. This is an NVIS pattern. You can see that our elevation angle is 90 degrees. The most gain on this antenna is straight up in the air. But it has pretty good gain straight up in the air, 7.75. And if we start to drop down a bit to show some angle in this antenna, now we're down to 70, there's 65 degrees, 60. These are useful angles for bounce, for one-hop stuff, for local NVIS stuff. So it's 60 degrees, 55 degrees, 50 degrees. We still have 6.6 dBi. And at 45 degrees, we still have 6.15 dBi. So this is not a bad antenna for local communications. This thing works really, really good. And in fact, that's what I have up in the air right now. And it does extremely well. But if you want to talk distance, you really would probably want to either get this antenna further up in the air or choose a different design. But this is a good first antenna. So let's roll on with this antenna design and see what else we can learn about it. So I'm going to check the standing wave on this antenna, and we can see it's quite good. I have 1.0 something at 7.25, 7.26 megahertz, and it covers the entire voice portion of 40 meters easily with an SWR of 1.5 or less to 1. So this antenna would be very good for a radio that does not have a built-in tuner. You could cover the entire band. And we're going to prove right now that this is not a multi-band antenna, because let's do a sweep that includes 20 meters and see what we can see. And there you can see it only has one resonance, and that's 40 meters, 7.3 megahertz in this case. That's the only resonance in this antenna. It is not a multiband antenna at all. It's good for one frequency. Well, this frequency, I should say, would probably work on 15 meters as well. So let's go ahead and check 15 meters and see if it is resonant at 15 meters. And sort of. It might work with a tuner at 15 meters, which a lot of hams will do. They will tune their 40 meter antenna on 15 meters, and it becomes a usable antenna at that point. But traditionally not a multiband antenna. Very simple to build. So simple current pattern on this antenna. You can see very traditional center-fed dipole. We feed it at the high current mark to try and get a good match to 50 ohms, and it ends up being a very good match to 50 ohms. Okay, now we need to talk about other designs. So if you do have a tuner or a matcher of some sort, then you can get into a multiband antenna. Something along the lines of this. So this is a current pattern example for an end-fed 40 dipole. So instead of feeding it in the center, we're going to feed it from the end. And this is a high impedance point, low current, high voltage, high impedance point, typically somewhere between 2 and 5,000 ohms. And there's matches that are provided by transformers at 2450 ohms, and then others as well. So a 49-to-1 would be 2450 ohms. So if you can get this end impedance to be close to 2450 ohms, these are great antennas because they are what we call a multi-band antenna that becomes resonant on more than one band. So these are the three current patterns of the three most common bands that we would see, not including 15 meters. We just have 40, 20, and 10. But you can see when we feed it from the end, that's going to be the high impedance, high voltage, low current point for more than one ham band. In this case, 40, 20, and 10 would all have their high voltage, high impedance, low current points at the end of the antenna. So if you feed it at the end, it will resonate on all three of those bands because all three of these bands are even harmonics of each other. So for 40, when we go 40 to 20, that's exactly twice the frequency, so it's an even number. And then when we go from 40 to 10, that's 4 times the frequency. We go from 7 megahertz to 28 megahertz. Once again, that's an even number. So these are even harmonics of the 40 meter band or 7 megahertz. And by feeding it from the end, it becomes a multi-band antenna. It's still a resonant antenna on all three bands. We just have multiple wavelengths on 20 meters and multiple wavelengths on 10 meters. A single current pattern on 40 meters. And these will resonate just fine and work. But because of end effect, they don't align perfectly. You'll find if you cut this for 40 meters, it's going to be slightly high on frequency on 20 meters and even higher on 10 meters. So that's the downfall of an end-fed antenna and an off-center fed antenna, which is our next example. So this would be the off-center fed example. So instead of feeding it from the center or the end, we're going to feed it at about the 18% mark or 20% mark. And the theory here is we're going to use either a 4-to-1 transformer or a 6-to-1 transformer at the feed point of the antenna. So 4-to-1, 4 times 50 ohms gives you 200 ohms. So we'll try and pick a point on this antenna where all three of these current patterns give us an impedance that's close enough to 200 ohms that it's usable. And you can achieve that. You can get close. So if your antenna is pretty close to the ground, you'd probably want to choose the 4-to-1 transformer because a 40 meter dipole that's close to the ground is going to push your impedance lower than what it would be on 20 meters or 10 meters. So the appropriate choice would probably be a 4-to-1 if you're not a half wavelength above the ground, which is 67 feet. But if you can get it up to 67 feet, then the 6-to-1 transformer might be the better choice because 6 times 50 ohms gives you 300 ohms. And because you're high enough above the ground, you're half a wavelength above the ground, the impedance won't be pushed down like it would be in the lower example, and that 6-to-1 transformer may work better. But basically the way you tune this antenna is you just start shifting the feed point back and forth. So you're trying to make it resonant on more than one band, and with a nano VNA or an antenna analyzer, you'll just start trimming one end and adding to the other end until you get all of the bands that you want to work at an acceptable SWR. And usually you can get them within a ballpark and make this antenna work with standing wave that's certainly less than 3-to-1 across the entire voice portion of every band that you want to work. But it does require a tuner. So these will require some sort of a matching device or tuner in order to use it. It will not work with a radio that has a very low SWR requirement. For instance, most EZUs require 1.5 to 1 or less. And this wouldn't be a good choice for something like an FT891 that does not have a tuner built in. But it would be perfectly acceptable for something like my 710, FT710 that does, or ICOM 7300, or any of the modern transceivers that have a built-in tuner would work just fine with this antenna and give you multiple bands. Okay, so probably should talk about tuning a little bit. I've heard it said that if you're low on frequency, that if you put this antenna up in the air and it's low on frequency, so let's say that we want to tune this thing to be centered at the lowest SWR at 7.2 megahertz. And we check it and it's 6.9 megahertz. Well, I've heard a lot of people say that you just trim equally from both ends. But that's not how I do it. What I will do is I will look at the SWR first. And if it's 1.05 to 1 at 6.9 megahertz, then yes, I would trim equally from each end. So I would take a foot off of each end of it and retest. If it's 1.3 to 1 at its lowest point, what I will do is I will trim one side at a time. Because what I'm trying to do is get a better match before I set the length of the antenna. I want to find where it matches up a little better than 1.3 to 1. So what I would do in that case is I would take 1 foot off of one end and then recheck the SWR. And two things are going to happen. It's going to go slightly up in frequency and the SWR is going to change. But we don't know if it's going to go up or down because we're just randomly picking one end of it to pull a foot off of. So if we pull that foot off the wrong end of that antenna, the SWR is going to go up. What we would do in that case is we would add that foot back and we would go to the opposite leg and take a foot off of that leg. And what should happen is the SWR should go down. Now this is all assuming that your SWR or your impedance is lower than 50 ohms, which is often the case when you have a 40 meter antenna that's low to the ground and it's an inverted V configuration, because both of those situations will try and force the impedance lower. Remember, a free space dipole has an impedance of about 70 ohms. When we start bending the legs down to make it an inverted V antenna, that's going to force the impedance lower. And then likewise, when this antenna is lower to the ground than 67 feet, it's also going to force the impedance lower. So typically when you take a 40 meter antenna that's only 30 feet in the air, you're going to check it and find if the SWR and the impedance is low. So the SWR would be high, the impedance will be low. And what you can do is just start slightly driving that antenna off center until you get that impedance up to a perfect 50 ohm match. So you take one end off at a time until it comes up to 50 ohms and centers on the frequency where you want it to center on. So once again, if it was centered on 6.9 megahertz and the SWR was 1.3 to 1, and let's say that I take 1 foot off the left leg and the impedance goes up and the SWR comes down to 1.2 to 1, and now it's resonant at 7 megahertz instead of 6.9 megahertz. So at that point, I know I'm moving in the right direction. So what I would do is take another foot off that same leg and once again watch the SWR and watch the center frequency and see if the SWR goes up or down. If it goes down, great. And the frequency will come up a little bit. Let's say it goes up to 7.1 megahertz. Okay, we're still a little bit low on frequency, so I would take another foot off that same leg. And let's say for some reason now the impedance decides to change in the wrong direction and the SWR goes up. So we were 1.2 to 1. Now let's say we're back up to 1.3 to 1. Well, in that case, I know I've passed up the sweet spot on this antenna. I would add that foot back and I would go to the opposite leg and take a foot off of that side. And hopefully the SWR would go down and it would end up at 7.2 megahertz and we would call this one done. And that's how I do it. You don't necessarily have to take equal lengths off of both legs if you're trying to hunt a better SWR reading where it's centered in frequency. Sometimes you want to drive it slightly off center, and you can actually get a better impedance in SWR match if you do that. Okay, that's true for any dipole, off-center fed, end fed, center fed. No matter what it is, you always want to play with the lengths on both ends, and that way you can try and force your SWR as low as you can get it, and try and center it up in the portion of the band that you want to use. And when I'm doing that, hopefully you've cut it long. If you've cut it short, that's going to create problems. But typically when you use that formula 468 divided by frequency, it will be long. And then when it's long, what I will do initially is I will take the wire and I will fold it back on itself and just twist it. Like so. So that made it shorter, but it didn't make it shorter by that length. It made it shorter by somewhere between that length and what you started with. In other words, if I did that and this antenna was suddenly resonant at exactly the correct frequency that I wanted it to be, and then I cut that wire right there, it would be too short. So what you have to do if you're doing it this way is you start trimming it a few inches at a time, and until you get to the point where that loop is right where you want it to be. So by folding it back upon itself like that, you're not shorting it, or you're not shortening the antenna by whatever that length that you fold it over is. In this case, this is about 6 inches. So you're not making the antenna 6 inches shorter. This does resonate slightly. So when you fold that back, all you're doing is you're trying to get it close. And then if you end up with a whole bunch folded back, you have to start trimming that at some point. So if I get more than a couple feet folded back like this, and I'm still low on frequency and I still need to trim it more, what I will do is start trimming this folded back section, and you'll actually see the antenna start getting shorter when you do that. So your center resonant frequency will start climbing as you trim that folded back portion off of it. And that's how I do it. And then once you get it perfect, you can just take that and fold it over and slide a piece of heat shrink over there and shrink that down, and it becomes a nice loop. And you can put this through some sort of an insulator. This is just cut out of an old cutting board, a Delrin cutting board. IKEA sells a good one to do this. Delrin is nice because it's very machinable. It's a soft plastic, so you can cut it with a jigsaw and drill it really easily. But you could make an insulator like this, and then heat shrink that, and then put your paracord on the other end of that and go to your anchor point. And that would be how I would finish off the end of that antenna. And in my case, I seldom use these because I'm in a very dry portion of the state. It hardly ever rains. And paracord, when paracord is wet, it does become a conductor, but very, very seldom is it wet where I live. So I usually cheat and just tie a knot in the paracord and tie it to the wire, and I'm good. And that's it. So the next step is going to be to build a balun box, and I'm going to set that up on the bench and we'll get started on that. I can show you how I do it. The parts are readily available. Most of the stuff comes from your local hardware store. The toroid you'll have to order online. But other than that, you can build these things yourself. There's tons of resources on YouTube to show how to build 4-to-1 baluns, 6-to-1 baluns, 49-to-1 baluns. You do not need fancy wire to build these things. This is a 4-to-1 balun that I've wired up. It just uses 18-gauge speaker wire, which is fine for a 100-watt transceiver. Works just fine. I've built 4 or 5 of these this way, and they all work great. The only time that you would want to use a fancy wire is if you were running power and this toroid would be overheating, and in that case Teflon wire might be a good option. But an even better option would be to increase the size of the toroid, so you could stack 2 of these together and then make your windings around both toroids, which would double your heat capacity, and you could probably get away still using that smaller wire. But actually, if you're going to make a 4-to-1 balun, and you were running power, I would probably want to run something a little bit bigger than 18 gauge. But anyway, like I said, on YouTube there's a bazillion resources for building these things. This is a 1-to-1, and this is a 4-to-1. And this is the one I'm going to put in the balun box that we're going to build, because the antenna that I'm going to show you how to construct is an off-center fed dipole that requires a 4-to-1 balun. So this is what I need for that. And I'll put the link for the build instructions for this one in the comments below, so you know what we're getting into. As far as balun boxes, I like to use these. These are hardware store items. You can get these at Home Depot or Lowe's. They're about $12, and they're waterproof. So you can drill a hole in the bottom, put an SO239. You can drill holes inside to put something to take the strain relief on the hanging wire. And on the inside, there's plenty of room for your balun. Goes right in there. So that's what we're going to do next. So I'll set up the bench and be right back. Okay, these boxes are traditionally made to be mounted like that, and they have these ears, and you would screw through and attach it to a wall or something. But I'm going to put this on a vertical piece of square tubing, so I'm going to rotate it 90 degrees. And luckily the box is perfectly square, so the lid will fit either way. And what I'm going to do first is I'm going to drill a hole right in the middle of this box for mounting purposes, because I don't trust these ears to hold the box in their entirety, because I figure once this thing's in the air for a few years they may get brittle and break off, and then my wire would be on the ground. So I'm going to drill a hole right in the middle of the box, and that's just going to be for an attachment screw. So I'm going to use 3 attachment screws, 1 in the middle, 2 on the ends. And that will do. The reason I'm doing that now is because I'm going to end up covering it up here in just a second. And the next step is to mount our SO239. So the SO239 is where we mount, or we screw our coax onto. So we need to drill 5 holes. We need to drill a big hole for the center part to index into, and then 4 smaller holes so I can put my screws that attach the SO239 to the box. And I'm going to start with the big hole. Step bits work really nice for this. Okay, that fits pretty good. Now I'll just drill the attachment holes. Okay, I need to think a second because this is going to mount, let's see, like that, and I want the positive wire to go this way, so I want my ground lug to be on that side. Okay, I've got that mounted. I've got my toroid prepared. So I've just soldered a ground lug here, which will go on one of these screws, and that will be the center. So I'll solder that in the center of that SO239. And then I've got these little pigtails of 12 gauge, so that when I attach my wires I can just use wire nuts to do that with. So we'll set that aside because now I need to do my strain relief. These eyelets will become the strain relief. we'll need to drill 2 holes somewhere about right here. I just need to leave enough room for this washer. Something about like that. And the way that we do this is the wire will come around like so. And we'll put a piece of heat shrink over it. We will shrink that down, and then this wire will drill a small hole. So this provides the strain relief, and this is just floating, and the hole that we drill will be very small. In fact, I can go ahead and do that now. And I drill these at an angle. Simply so the wire runs out and down. So it'll go just like that. And then we'll wire nut it right there. Good to go. Go ahead and do the other side. And that will be our strain relief. For now, I'll get those out of the way because I need to chase up 2 more of these nuts, which I probably have out in the shop. For now, we'll go ahead and we will mount our toroid for the final time. And there we go, we are almost done. Now all I have to do is just anchor it somehow so that it doesn't flop around inside the box. And the way that I do that, I just use a little bit of silicone. I'll put a dab of silicone in here, trying not to cover up my hole. And then I'll just rest that in there like so. Once that silicone sets out, it will be fine. And I like doing that instead of using glue or epoxy because if I want to take it apart at a later date, I can just pull the silicone apart and start over. So our finished balun box is going to look something like this. So that would get wire netted to that. And we'll do the same thing on the other side. And there you have it. It is really that simple. So then I would bring the wires through the loop for strain relief. I'd go into the box. I'd wire nut these down. I would screw the lid on. I would bolt it to my upright, whatever that is. And then all you need is enough wire to complete your antenna. So on this antenna build, I'm going to be using, I believe this is THHN. Yes, THHN wire. This is going to be 14 gauge. And this is a 500-foot roll. The antenna I'm going to build is that monstrous antenna that's 270 feet long. But I would cut off my lengths, I would wire them in, I'd mount it up in the air, hook up the nano V-Nay and start trimming. And that's what we'll do in the next video. Thanks for watching.